Well, I was just making a recording and right at the end, my screen froze. That's sad, but we'll start it again. I have some of the stuff already entered in my calculator. Maybe that'll speed things up a tiny bit, but our plan here is to look at these four patterns of 4 points. And the question is, could we see that sort of association just randomly? So could this just be a random scatter of points, or does it look like there's a pattern of decrease as x increases, decrease, decrease, increase? Which of these legitimately show a pattern that probably wouldn't have happened by accident? So we could pursue further the connection between x and y if all we have is these 4 values. So for 4 values, if you see this, you go, I don't see anything, I don't see anything, I don't see anything. Here I do see something. Now, sometimes I'll see this type of information presented where the bottom part is years. And this is a pattern of something like, oh, maybe that is retention rates over time. They seem to be decreasing. Oh, look, retention over time seems to be increasing. Or here, what happened? And the question is, well, would that kind of stuff just happen at random? And this particular procedure answers that question. A consistent increase like this is unlikely to happen randomly. This might be unlikely randomly. These just look like the random patterns. And the plan is to compute the correlation coefficient. Since it tells the strength of linear relationships, maybe it says whether that relationship is not due to random variation. It's strong enough, it's not due to random variation. So we read here, first we need to see a possible linear pattern in the scatter plot. These are all possible. The correlation coefficient gives us a way to determine whether there's evidence of some, although possibly weak, linear association between the 2 variables, or whether the pattern could be due to chance alone. And the plan is to take the data and compute R. So I'm in here. That's fine. Maybe I'll put it here so we can see the whole thing, because all you have to do now is see the data. Okay, so I'll go to stat. I'll go on first. Go stat, edit. And what I've done is I put the x values 1, 2, 3, 4. They're all the same for these, into list 1. And then I put the y's into separate lists. So that's list 1, list 2. I guess I'm writing it here. List 1, list 3, list 1, list 4, list 1, list 5. That's where I put the information. So for example, list 5 here, 6, 14, 11, 10. That's 6, 14, 11, 10. So I've done that across the board. And then we can go ahead. I'll get out of here. Second, quit takes us out of there. I'm going to go to stat calc. And we said the place where we get correlation right now is down here at regression. And we get to regression, we have to pick x and y. So I go here. So second one is x. Then I go to the next one, enter. Second 2 is y. And then I scroll down to calculate and do it, enter. So 9, 6, 4, 7. So that pattern has that correlation. And we go back to stat, calc, regression, enter, and then I'll go, list 1 is good, but now I'll change it to list 3, second 3. Go down, go. So now I got negative 0.3282, negative 0.3282. So we said correlation tells you strength and direction. A positive R says there's a positive association. A negative R says there's a negative association. So we see that here. And the closer R is to 1 or minus 1, if it's negative, close to negative minus 1, if it's positive, close to plus 1, the more linear the data should look. So 0.967 looks quite linear. Negative 0.3282 doesn't look very linear. Okay, and then so that's making sense. And we'll come on down and now we'll do list 1, list 4, stat, calc, enter. Oh, wrong one. Stat, calc, regression. Now list 1 is already there. We're doing list 4, second 4. Go down, go. 0.7442. 0.7442, like that. And finally, list 1, list 5, stat, calc, regression, list 1 for x, second 5, list 5, it said list 5 here, list 5 for y, go down, calculate. 0.3517, 0.3517, okay. So now it's time for the big reveal. We have a table that we provided that tells you the critical values. So we use this name critical values often in statistics. It says if the value of R is not larger than what we call the critical value, either larger in a positive sense or more negative, because R could be negative. It just only has positive numbers. So an R bigger than this or R less than negative that for this sample size, this many points on this column, says that that pattern, probably not just random, it's probably due to a linear connection between X and Y. So we say if it's larger than critical value, if it's not larger, we say no evidence of a linear association. Otherwise, say there's some evidence of a linear association. However, the value of R is not resistant to outliers. This means a single outlier can make us think an association exists. So we take a look at the graph first and make sure there's not outliers influencing the value of the correlation. And once we see that, as we see here, these all look like pleasant little graphs without outliers. Then we can use the value of R to determine whether the pattern's strong enough that it looks like there's a connection between X and Y. And so we come in here, the number of this N here is 4, the number of points. So that says the critical value is 0.95. So it says we need R larger than 0.95 or smaller than negative 0.95. So like more negative than 0.95, like -1 would be, oh, -1 would definitely work and that'd be perfectly linear. So it has to be pretty close to being linear for us to claim with only 4 points, we see a pattern, right? You imagine with 2 points, you always see a pattern, so that can't work very well. With 4 points, it's pretty easy to have a pattern randomly, so it has to be a pretty strong linear pattern before we claim there's a connection between X and Y. We have to beat 0.95 or minus 0.95 for R, okay. And then we come back to our calculations and see which of them are larger than 0.95 or smaller than minus 0.95. 0.96 is bigger, we're good. That's not as small as 0.95, not good. 0.774, not big enough. That should be negative, right? It looks negative. I'm scared now. We'll go in here, stat, calc. I must not have seen it. Linear regression. This is a 1 and 4. List 1, second 4. Down we go. Calculate. Negative. Oh, you see that? I just didn't copy it. So, so it's not big enough. I put an X here. Not big enough. Okay. And then 0.3517, not big enough. So the only one that appears strong enough that we think it's just, there's not a very good chance at all that just randomly would happen is that one. These, even if there was no connection between X and Y, are the kinds of patterns you might see. These kinds of correlations are the correlations you see in 4 points with no connection between X and Y. This one doesn't happen unless there's a linear association between X and Y. Of course, it could possibly happen. It's very unlikely to happen if there was unless there's a linear association. So we're going to claim here, we're pretty sure this pattern wouldn't happen due to chance alone. And so we're going to say, as far as we know, based on those 4 points, which is not very many, it looks like X and Y are linearly related. Kind of cool. And that's how statistics kind of works. It's trying to screen out random stuff from stuff that isn't random. So we say these are likely random, that likely isn't. So we say they're linearly associated. And I survived that with no crash. That's exciting. And I'm going to stop this recording. And then pretty soon we'll be on to a new chapter. Or not a new chapter, that'd be wishful thinking. A new section. We'll see you in a bit.